Have you ever just sat by a calm pond on a summer day? If you look real close, you'll probably see them. These little insects just gliding across the top of the water like it's solid ground. They dart around, they stop on a dime, they literally dance on water. This is the water strider, and it looks like it's completely breaking the laws of physics. I mean, you gotta wonder, right? How does this tiny bug, which is definitely denser than water, treat the surface of a pond like its own personal skating rink? What is going on here? Is it some kind of biological magic trick? Well, let's dive into it. It's not magic, it's something way cooler. It's a breathtaking masterclass in how physics, biology, and technique can come together. We're gonna break down the science behind this incredible feat, piece by amazing piece. All right, so to get how the strider works, we first have to understand the world it lives on. See, the surface of the water isn't just a boundary. It's a dynamic, physical landscape, and it has its own set of rules. The number one rule here is something called surface tension. The easiest way to think about it is like a trampoline. Water molecules, they really like to stick together. And right at the surface, where there's no water above them, they pull on each other extra hard, creating this tight, elastic-like film. This skin is what the water strider is standing on. So the strider rests on this trampoline, making a little dent in it but not breaking through. But here's the thing, just having surface tension isn't enough to explain it. I mean, you can float a sewing needle on water, but it can't zip around, right? This is where it gets really interesting, because the strider's body is specifically engineered to interact with this skin in a totally unique way. The strider's first secret weapon is a property with a big name: super hydrophobicity. Now, this isn't just waterproof like your rain jacket. No, this is an extreme, almost total rejection of water. We measure this with something called a contact angle. Basically, the higher the angle, the more a drop of water beads up and refuses to get a surface wet. And the water strider's leg? Get this. It clocks in at a contact angle of about 168 degrees. For perspective, anything over 150 degrees is considered super hydrophobic. This makes its legs one of the most water-repellent surfaces anywhere in nature. The water literally can't get a grip. But here is a key detail. Not all waterproof surfaces are created equal. You can have a rough surface be super hydrophobic in two ways. There's the Wenzel's state, where water kind of seeps into the little cracks and grooves. That makes water droplets get pins down, making it sticky. But the strider? It uses a much smarter solution, the Cassie state. Here, the surface texture actually traps a layer of air, so the water sits on top of this air cushion almost like a hovercraft. It can just roll right off with practically zero friction. That is the strider's secret sauce. So how does it achieve that perfect Cassie state? Well, to answer that, we have to look at the strider's anatomy. The key is in the incredible multi-layered structure of its legs. It's a marvel of microscopic engineering. Okay, if you could zoom in on a water strider's leg with a super powerful microscope, you'd find this amazing structure within a structure. The leg itself is covered by thousands of microscopic hairs, or bristles. But it doesn't stop there. If you could zoom in on one of those bristles, you'd see it's carved with even tinier grooves on a nanoscale. It's this incredible, repeating, hierarchical design. And that is the genius of it. The bristles and their tiny nanogrooves create this complex forest that traps a permanent layer of air all around the leg. This air cushion makes sure the leg itself never actually gets wet. It's like it's wearing a permanent, perfectly fitted life jacket. And that's the key to maintaining that super slippery Cassie state. So what's the result of combining that water trampoline with this incredible super water repellent leg? It's just astonishing. A single leg of a water strider can support up to 15 times the insect's entire body weight before it breaks the surface. That is a massive safety margin, and it's why they can move so fast and so dynamically without ever sinking. So, we've established the legs are basically unsinkable. That's amazing. But being able to stand on water is one thing. Moving around effectively is a whole other challenge. How in the world do they push off a surface that has almost zero friction? Well, water striders basically have two gears. First, there's rowing. This is their calm, stable motion, where they use their middle legs kind of like oars. It's for casual cruising and changing direction. Then there's leaping, a powerful, explosive burst of speed using both their middle and hind legs. That's for catching prey or making a quick getaway. And this brings us to the next huge question. I mean, on solid ground, you push against the ground. You use friction. But on the water's ultra-slippery, super hydrophobic surface, what is there to push against? For a long, long time, this question completely stumped scientists. This puzzle actually got a name, Denny's paradox. For a while, the main theory was that striders pushed against the tiny waves they created on the surface. But the physics showed you had to move your leg faster than about 23 centimeters per second to even make those waves. And the thing is, young, small water striders, they just couldn't move that fast. So physics itself seemed to be saying that they shouldn't be able to move at all. The big breakthrough finally came in 2003. A research team discovered that the solution wasn't on the water surface at all. It was just beneath it. They found that as the strider sweeps its leg, it creates something else entirely, something you can't even see from above. And what it's creating are these tiny, swirling whirlpools, or vortices, under the water. You can picture it, right? It's just like when a canoe paddle pushes through the water and creates a little vortex behind it. The water strider is literally pushing off of these powerful underwater structures that it creates with every stroke. And these vortices aren't just some small side effect. Oh no, they are the primary engine for the water strider. Experiments have shown that these underwater whirlpools are responsible for transferring the vast majority, like up to 90% of the momentum that actually pushes the insect forward. The little waves on the surface, they're barely doing any of the work. So figuring all this out is more than just solving a cool biological puzzle. By taking apart how this tiny marvel works, we can actually learn some pretty profound lessons in engineering and material science. When you put all the pieces together, you really see the sheer elegance of the design. Every single detail is optimized. The legs are flexible so they don't pierce the water skin. The bristles are tilted just right to reduce drag when they lift their legs up. The whole layered structure is built to create that perfect air cushion. Even the way they rotate their legs when they jump is perfectly tuned to get maximum takeoff speed. It's just perfect. And you can bet this masterclass in natural engineering has not gone unnoticed. Researchers are actively mimicking these principles right now. We're starting to see the development of tiny aquatic robots that can walk on water, new kinds of super water-pooed materials inspired by that Cassie state, and even low-friction coatings for everything from ship hulls to medical devices. You know, at the end of the day, the water strider is just this humbling reminder that nature is often the world's most innovative engineer. Over millions of years of trial and error, it has produced solutions to incredibly complex physics problems that are way more elegant and efficient than anything we've come up with on our own. It really makes you wonder, doesn't it? As we've seen, a simple insect on a pond can hold the secrets to next-generation robotics and material science. It leaves you with one final thought. What other incredible wonders are out there, hidden in plain sight, just waiting for us to look a little closer?